So now we're going to move into the next algorithm for finding maximum flow. And historically, this came about, I think, in the either the late 1970s or the early 1980s. The Ford-Fulkerson algorithm, I think I told you, was developed either in the 1940s or 1950s. And there were some improvements. Actually, a question was asked, I think on the first day I started talking about Ford-Fulkerson, about whether there's a way of picking a good augmenting path. And in fact, the book covers that. There are a couple of pages that show, for example, that if you take the shortest augmenting path, the one that has the smallest number of edges in it, not shortest by capacities, but just the number of edges, then the algorithm terminates in a time that is not dependent on the size of the capacities. So it's just dependent on the number of nodes and perhaps number of edges. But at any rate, we're not going to look at that. You can read that for yourself if you like. But we're going to go to the next step, which is called the Preflow-Push Algorithm, which was really a very surprising algorithm when it first came out. And I'm not remembering precisely the history. I'm thinking it was developed by a graduate student at Berkeley, but named Andrew Goldberg, but it may not have been. But he certainly was very involved in that later on. So in a preflow is not quite a flow. So let me give you the basic definitions. An ST preflow, it's again an assignment F of a value to each, or not, it's a non-negative value to each edge E, so FE greater than or equal to 0. And in fact, FE is going to be less than or equal to CE greater than or equal to 0. Well, this is the same capacity constraint that we had for a flow, so that doesn't change. So we're still talking about an assignment of non-negative values to each edge, and this is the same constraint we had before. But previously, we had, for all nodes V, other than S and T, we had that the summation flow E into V, flow E out of V. What did we have here previously? That was equality, and that was called the conservation constraint. Now what we have is that the flow into V has got to be greater than or equal to the flow out of V. So somewhat relaxed the conservation constraint. And so you can just imagine this is saying that if you think about liquids or whatever you think physically, whatever it is that's flowing into V, some of it disappears, or could possibly disappear, but nothing ever just materializes. Okay, so if it's current that's flowing, then some of it gets dissipated as heat or whatever current does. If it's water, some of it leaks out, whatever you want. But nothing magically just appears. Okay? So all right. That's what a preflow is. And what this algorithm is going to do is always maintain a preflow. Instead of maintaining a flow, it's going to be manipulating and changing these assignments so that there's always a preflow in hand, but not necessarily a flow. And then at the moment when the algorithm has a flow, well, we know it's a flow when this is equality. Okay, when this inequality becomes an equality, then you have a flow. At that moment, it'll turn out that the flow that the algorithm has is actually a maximum flow. All right, so I need another definition before I show you anything more. about the algorithm, or actually EF is equal to FE minus summation FE. This is into E. This is, sorry, into V. So why isn't there a V here? Yes, there is a V here. So the excess flow into V, that's the amount into, out of. So the amount that comes in minus the amount that comes out, that might be positive, or it might be 0. But that's the excess that, it really would be better to call it the leakage or something, because that's the amount that disappears. But anyway, it's called the excess at V. All right. As we noted a minute ago, if EF of V equals 0, then F is a flow. Okay. All right. Another definition. H of V is equal to the height of node V. At this point in the book, they try to give a physical analogy or intuition for what this algorithm is going to do. If you think of these values, well, I should say every node is going to have, every node V is going to have an HV associated with it throughout the algorithm. And the book tries to say that these are like heights, physical heights, and that water is going to be flowing downhill, and you want the height of one node to be higher than the height of another node if it's going to have a flow to it. That isn't quite what happens in the algorithm. So the intuition, the physical intuition doesn't quite work. But they call this a height in order to try to make it work. Okay, but we're going to have H of V is always going to be greater than or equal to 0. And in fact, one more definition, I think. And we can actually prove something if we have time. Probably not.
I'm sorry, you're deferring the actual definition of height later, right?
Well, okay, so this is I'm just naming this thing. This is going to be named the height of V. And every node V will have an HV value during the algorithm. So I'm just naming that there's some variable here for each node V that's going to be used throughout the algorithm, and I'm going to call it the height. Okay. Well, yeah, I'm not going to be able to prove what I wanted to prove, and it would have been a natural stopping place. So I'm going to have to pick this up next time. Try to review these definitions before Friday, because I don't want to waste a lot of time next time repeating the definitions. But if you don't have the definitions in your mind, it's not going to make a lot of sense. The Friday's lecture isn't going to make much sense.